Okay. So, hello. We're going to finish up the chapter 12 stuff we were doing last time. Let me... You know what? Never mind. There's too much going on. So, I had drawn it differently during the last SI session, but I cleaned it up for you guys a little bit, and I put it into the handout format, just so you could see how I want you to fill everything out. And just to review what we covered last time, we did oxidation, and we basically said that primary alcohols can either turn into an aldehyde or they can go all the way to a carboxylic acid. And we know that if it's a strong oxidizing agent, it goes all the way. If it's weak, it stops at the aldehyde. And we also know that secondary alcohols are always going to make a ketone no matter what reagent you use. There's also no tertiary alcohol here because tertiary alcohols in this class cannot be oxidized. So someone asked, where can I find this sheet? It's supposed to be on my Canvas page. It's entirely possible that I didn't upload it last week because I was just so out of it. I will, if it's not up there, I will upload it right after this session. So I do apologize if you guys don't have it yet. But it will be up on my Canvas page later. Also, someone mentioned last time that there were SI handouts on Dr. West's Canvas page. And so I just looked at it, and it was actually the ones from last semester. Joe was the SI leader last semester because I took a semester off. They are wonderful. I believe it's like almost the same handout that I used, but I just didn't want you guys to get confused, so I unpublished it so you guys can't see it, and I will upload all of mine onto his as well in case you guys can't see it on my Canvas page for some reason. So I will do all of that today. Thanks for bringing that up. Okay, so then we talked about the oxidizing agents. We said that PCC and DMSO are both weak, and then all this different stuff is strong. And I basically told you guys to remember, if it's 4 or more oxygens, it's strong. If it's anything else, it's going to be weak. So that's how I want you guys to think about it. All right, so we started talking over here about all the steric hindrance and reactivity of carbonyls and stuff, so I'm not going to go over that again. I don't know why I didn't write it in, but we talked about it last time. So I did want to reiterate this because we stopped at reductions last time. So we know that our reducing agents come in weak and strong, just like our oxidizing agents. And we said that NaBH4 is weak, LiAlH4 is strong, and I told you it's because A comes before B, so A is stronger than B. And we talked about group 1 versus group 2. So can anyone remind me what in the world group 1 and group 2 are? I'll write it in the corner. Does anyone remember? Okay. Aldehydes and ketones are group 1. Yes. And someone else said they're very reactive. Exactly. So they are more reactive. Perfect. And then so what's left over for number 2? Yeah, carboxylic acids. And esters. Sweet. And we know that these are less reactive. Perfect. All right. So the other thing that we talked about was Daiba. And this usually comes back for the final. It's not on this exam, but I do want to point it out here. So it's only going to react with group 2. So only these guys. And it's going to stop at the aldehyde. So we kind of say it's a weak, strong kind of in between there. So now we're going to kind of go into reaction mechanisms, and we started this a little bit. So can anyone tell me, let me zoom in, what is the reducing species? So this is our reducing agent. What's our reducing species? Does anyone remember? So another way I can ask, oh, yes, there we go. So the reducing species is the H minus. You are correct. So the H minus is what's actually doing the attacking. So we're going to do this. Bam. The electrons are going to go up. So we end up with O minus because it gets an extra pair of electrons. And we added a nifty little hydrogen here. So now we're left with this negative charge. What can we do to get rid of the charge? What's an easy way? Yeah, exactly. So someone said you use the H3O plus. So I'm going to go ahead and do that in pink. So we take the H3O plus and we're going to protonate. So it's going to protonate the oxygen, and it essentially means it stole a hydrogen. So now it's back to 2 pairs of electrons. It has a hydrogen, and we can't forget the extra H that we just added there. So we went from an aldehyde to what kind of alcohol? Primary, secondary, or tertiary? Primary, yep. So in the corner, I'm going to write aldehyde is reduced to a primary OH. Now, I want you guys to tell me how you think the mechanism would go for a ketone. So someone either walk me through it like verbally or however you feel. And then someone said, so will this always happen? So like, do you mean whether you have whichever like reducing agent, or what do you mean exactly? Like whether we have this reducing agent or LiAlH4, it's going to be the same exact mechanism. And okay, so yeah, it will always basically go from an aldehyde to a primary alcohol if we have NABH4 or LiAlH4. You're welcome. All right, so who wants to help walk me through this second reaction? And you guys can all do it. So what's the reducing species again? H minus, sweet. So anything with a negative charge is a what or a what? A base or a nucleophile. Awesome. So in this case, since it's going to attack, is it acting like a base or is it acting like a nucleophile? A nucleophile, awesome. So once it attacks the carbonyl carbon, what happens to that double bond? So I'll draw it out for you. So what is happening to that double bond? Someone said it breaks and it moves up. Perfect. So it breaks and it moves those electrons up. Absolutely. So we get what kind of charge? On the oxygen? A negative. I absolutely agree. Okay, so now we have a negative charge. What are we going to do about it? How do we get rid of the plus charge? Yeah, so we have an H3O plus, right? And so what's the buzzword? What are we going to do to the oxygen? So, okay, so one person said protonate, one person said deprotonate. So technically both of those are correct depending on what you look at. So we are going to talk in reference to this oxygen. So this oxygen will be protonated, and it's going to do that by deprotonating this acid. So technically you're both right, but I was kind of more looking for protonate because we're more focused on what's happening to the oxygen on our molecule that we care about. So right here. So we're going to protonate, and we go ahead and turn that into a O with 2 lone pairs and a hydrogen. And we also have to remember our hydrogen here. So, what kind of alcohol did we form? Primary, secondary, or tertiary? Secondary, yes. So let's go ahead right here and say that a ketone will make a secondary alcohol. And now that we've drawn that out, we can see up here the answer to these two. So we know when reacted with a reducing agent, aldehydes are always going to form primary alcohols. And we know that when reacted with a reducing agent, ketones will always form secondary alcohols. So, ta-da, we got that part. Now, I will give you guys a second in case you want to take a screenshot or finish writing down notes or anything. And then we're going to go and draw out group 2 reactions. And so someone asked, so we deprotonated in both mechanisms. So yeah, again, I want to use the word protonated because if he asks you a question, he's always going to talk about this guy, and I don't want you guys to get it wrong. But yeah, so we protonated the alkoxide and we turned it into an alcohol in both mechanisms. Any other questions? That was a really good one. If not, I can put my sweater on and then we can move on. Okay. I don't know why I have all that garbage written there. That's fine. Alright. So, I think I'm going to run out of room, so I'm just going to go ahead and open up an extra page. And I'm going to do these 2 reactions. I believe you guys don't have the handout anyway, so it doesn't really matter, but I will give you the same example so that you can fill out the handout and you're not lost. Okay, So, actually, before we even start the mechanism, what functional group is this guy? An ester, perfect. So, what group is the ester part of? I'm sorry, this isn't funny, but someone wrote S and then the next message ter, and I don't know why that cracked me up so much. So yes, this is group 2, and we know that group 2 is less reactive. So if it's less reactive, which reagent are we going to use? LiAlH4 or NaBH4? Yes, exactly. LiAlH4, and we have to use that one because it needs the more reactive substance. So H3O plus. But we know that our reducing species is still going to be the H minus. So it's always going to be the H minus. Don't mind me color coordinating. It just makes more sense to me that way. All right, so pretty much the same first step. We attack this guy. We move those electrons up. So we get bam, bam, bam. And we add a hydrogen. So now, at this point, what are we going to do? Can a brave soul please tell me what happens at the second step? Okay, one person says protonate. What does everyone think? I mean, that's what we've done the past 2 times, right? Wrong! It's a trick! Ha ha! I'm sorry. Okay, someone else actually already got it, so I guess I didn't trick anyone, but that's okay. Don't be sad if you were tricked. The audacity, I know. Okay, so the difference here is that we have this thing, right? This is different than a carbon or a hydrogen because, as someone said, it is actually a leaving group. So this thing, unlike a carbon or a hydrogen, can act as a leaving group. And this is a great question. Someone said, how do we know when something's a leaving group? So I will make like a little box and make a note. Stay. Okay. So carbons and hydrogens are not leaving groups. They're essentially never going to be a leaving group. Asterisk. Until chapter 19. But we're not at chapter 19, so we are going to ignore that for now. And until chapter 19, carbon and hydrogen are never going to be leaving groups. And we can say any heteroatom, basically, can be leaving groups. And another way we can say that is electronegative atoms. And we know that's because they have weak bonds. So anything like, let's say, an OH, an O with an R group, a nitrogen, a sulfur, anything like that. Those are all going to be leaving groups. We also know that not heteroatoms. What do we call those guys? Halogens. So any of the halogens can also be leaving groups. Yeah, for now that's good enough. So anything like this can be considered a leaving group, and that's because this bond right here can be broken. So this is a weak bond, it can be broken. And so this whole thing acts as the leaving group. And I might as well note this while we're here. So we know that being negatively charged makes something nucleophilic or basic. And we know that being protonated, aka plus charged, makes a better electrophile and a better leaving group. So we're going to talk about this a whole bunch between now and the rest of the semester, but keep this little note in mind. That'll be very valuable to you. So yeah, this goes back to Grignard's. Grignard uses these same exact concepts. So yeah, it is sort of like a Grignard. We haven't done Grignards. I showed you guys the video for it. I would really like to cover it. I just need to make sure that like time permits for it. Like if I ask 2 extra SI sessions and we're still super behind, we won't cover it, but I really hope that we will have time to cover it. Any other questions? Okay, so someone asked a pretty great question. What do you call the molecules that are actually being oxidized or reduced? Are they like substrates or what are they? So, we could, I don't think there's like a specific name for it. I just call it the reactants. I don't think, I mean, there could be like in actual chemistry, like in practice, I'm sure they have specific names, but as far as this class goes, you can call them reactants or substrates. That should be good enough. Good question, though. Okay, so sorry, that yawn took me by surprise. So, as someone mentioned, I don't remember who it was, I apologize, but yes, so now we're actually going to bring these electrons back down, and we're going to kick off the leaving group. So, does anyone have any idea why we would prefer to do this rather than protonate? It's something we've sort of touched on, but we didn't really cover it explicitly. So yeah, it's going to come back to reform a double bond on the center carbon, and then someone is kind of alluding to like, oh, well, that means there will be too many bonds. That's why we have to kick off the leaving group. So yes, that's a good point. That's why the leaving group gets kicked off. But why form the double bond instead of just making an alcohol? If you don't know, that's okay. Basically, do you guys remember when we talked about stability and how SP is the least stable, SP2 is the most stable? Oh, wait, excuse me. We talked about how SP3 is going to be less stable than SP2. So having the double bond would create an SP2 carbon here, which would make it much more stable than this SP3 conformation. So when we reform the double bond, we've reformed SP2 from SP3. And since we got rid of the leaving group, now this hydrogen is left. Any questions? Did that sort of kind of make sense? I know this tends to be where people kind of get a little bit confused. If you have any questions, please do not be afraid to ask. I'm going to zoom out and I'm just going to move this note a little bit down so that I have enough room to finish the reaction. Alright, so I kind of spoiled it, but we're not done with the reaction yet because this is a really, really, really strong reagent. So what do you think can possibly happen now? We can protonate, but what are we going to protonate? The oxygen? Sure. So, like, if we if we were to protonate this, we could get that, right? And what now? You know what? Fine. I'll draw it better. Because that's not a completely unreasonable way to go about it. So, we do have acid, right? So, and then they said, got me there. So, we have the acid, right? And let's say we steal it, we break that bond, and now we have protonated this guy. So when we talked about that little note, we said that being positively charged can make it a what or a what? I I was like looking at the chat and people are having a really funny conversation about like knowing each other's siblings and whatnot. I'm not getting in your business, but that's just funny. Okay, so someone said a negative charge is a base or a nucleophile. Yes, but if it's positively charged, I'll give you a little hint. Positively charged can tell us that we're going to be electrophilic or a better leaving group, things like that. Okay, cool. So we have a positive charge. So we made this more electrophilic. Awesome. What does that mean? What can we do now? I'll start awkward dancing again. No, I won't, but... Alright. Come on, peoples. Okay, someone said restate the question. Okay, so... We have this, right? We made it more electrophilic. That's cool, right? But we're not going to keep it like this. This isn't the end. So we can either deprotonate and go back to this, or we can go forward with the reaction. What could we do to move the reaction forward? Something that might help is if you try to figure out what we have left in the reaction mixture. So what do we have in the mixture? Yeah, we have LiAlH4, which is a whole mouthful. What else do we got? H3O plus, yeah, we have some extra acid. And let's not forget, we also have our side product, which is the alcohol, right? It's not really important. Just, I know someone always asks about it. This is a byproduct, and we don't really care about it. So, you guys have the answer right here. What can these reagents do? Starts with an R. Reduce. Yes, sorry, that was a big yawn. So we're going to reduce it all over again. So we have our nifty reducing species. And we're gonna bam pow, and ta-da, and ta-da. So basically, what you guys did, instead of reducing it and then protonating at the end, you just protonated it first and then reduced it, which is completely fine. Either one can happen in real life. So you guys got to the right answer towards the end. Does it sort of kind of make sense how we got from point A to point B? I'm going to take... Someone said I'll just rewatch it. Okay, well... Does it at least make a little bit more sense than when you came in today? Because that's all we can really hope for. Yes, okay, cool. I can live with that. Alright, so yeah, it's one of those things that you should watch once or twice just to really get an understanding. Reaction mechanisms are really hard. But, you know, I try to simplify it as much as I possibly can, just so you guys don't have to know, like, all the real background chemistry. So, in summary, we can basically say that ester has to react with LiAlH4 to make a primary... a primary alcohol. And I don't want to redraw the entire reaction mechanism because it's just a lot of work, but the exact same thing will happen for carboxylic acid. So if we were to substitute this with a carboxylic acid, we would have the same exact steps, and we would end up with the same exact product. So I'm going to say carboxylic acid plus LiAlH4 gives you a primary OH. And someone said a great comment, group 2 can't react with weak reducing agents. That is correct. So they can only react with the strong, which is LiAlH4, and it can react with Daiba, right? But if it reacts with Daiba, it stops here. So I will make a note of that. I'm really glad you brought that up. So esters and carboxylic acids plus Daiba equal aldehyde. Ta-da! All right, so let me zoom out so you can just take a look at all of this together. Any other questions or comments or concerns? There, I'll move it up a little bit. You guys did really, really awesome today. I know it's a Monday. I'm kind of not as enthusiastic as usual, so it's a little bit bleh, but I am really proud of you guys. You've been doing super good. Okay. If no questions, let's go to the next page. And this is something we already talked about, so reducing agent plus ester, we get primary alcohol, and the same exact thing for carboxylic acids. We have done this one basically. We did this one because it's the same exact thing. And we're going to go over this next time. I don't want to start it because we don't have enough time left for today. But I want you guys to try to do this on your own and come in with some ideas next time because it is kind of fun. And I use the term fun very loosely, but yeah. Long story short, I want you to look at it so that you guys aren't tricked when I give you the thing. Let's see. We only have 2 minutes left, so I kind of want to do a practice problem. Let's do this one. Alrighty, so get used to this because this is how questions are worded on the exam. It's all in this like condensed formula. It's ugly and I hate it. So I want you to take a second and draw this out for yourself, and then I will draw it out too. But you guys have to get used to reading in condensed formula. And then someone said it's gonna be a pain equals fun. Exactly, you get me. No, it's fun when things that are supposed to be a pain turn out to not be as bad as you thought they were. Okay, so I know that was only like a minute, maybe, but what functional group is this? It's one of the ones that you guys should know by heart. Any guesses? Carboxylic acid. Okay, let's draw it out. So we have 1, 2, 3, 4, 5, 6, 7 Sorry. 1, 2, 3, 4, 5, 6, 7. On carbon 1, 2, 3, 4. We have a ketone. And then on carbon 7, we have O2. And when you see that O2, it's going to look like this. And we have an O2CH3. So it's going to look like that. So it's not a carboxylic acid. It's very similar. It's a what? Ester, exactly. So we're going to say ester. And it's exactly the same here, so it's going to be an ester. A carboxylic acid would be CO2H. So very close. Sorry, my screen keeps being stupid. All right, so we go from this to that. So how do we go about figuring this out, right? It's saying what reagent would be used to do this transformation. This is the reaction they show you. And so what has happened? And I want like the simplest. Yeah, OH is transformed. OH is formed, yes. So what's it called when we go from a double bond to oxygen to a single bond? Well, yes, it was protonated, that's true, but reduction, yes, that's the one I was more looking for. So we did a reduction. And so which of these answer choices can we automatically get rid of knowing that it's a reduction reaction? C, exactly, because O4 means what? What does it mean if we have 4 or more Yes, it's oxidizing, but is it strong or weak if it has 4 or more oxygens? It's strong, exactly. So we know this is for sure not it. All right, and then someone made a really good point. It kind of went away in the chat, but they said something along the lines of, this one was reduced, but this one was not. So let's think. Ketone, is that group 1 or group 2? Yes, ketone is group 1. And ester is same or different group? Yeah, it's group 2. So we know that group 1 was transformed, and we know that group 2 was not. And we know that group 1 is more reactive, and we know that group 2 is less reactive. So, did we use a strong reducing agent or a weak reducing agent to only transform one of these guys? What do you think? Weak. Absolutely, I agree with you. And so, which one of these choices is weak? A or B? A. Absolutely, I totally agree with you. So we had to use a weak reagent in order to only reduce the group 1 and not reduce the group 2. Perfect. Any questions, comments, concerns? So it couldn't be D because if we use a strong reducing agent, it would reduce both of these, so we would not get this answer. If we use that one, we would actually get 2 alcohols. You're very welcome. Alright, so that's all I had for you guys today. Besides the Grignard reaction, we should be pretty much done with chapter 12 now. I will send you a weekly email either tonight or tomorrow morning that talks about everything we're going to do this week. But if you have any burning questions, you can let me know before I let you go for the day. I am going to stop sharing my screen though. Does anyone need me to scroll back to anything before I stop sharing? Okay, sweet. So yeah, that's all I have. I will stay for an extra minute if anyone needs me to, but have a wonderful day. You're welcome. Bye-bye.